Hi everyone. Today I am presenting my work on investigating the predictive reproducibility of federated graph neural networks using medical datasets. This work has been done at Basira Lab by myself, Dr. Arwa Rekik, and supervised by Dr. Islam Rekik. Given a pool of GNN models and each number of hospitals where each one of them has a local dataset, how to increase the model accuracy and reproducibility in terms of top discriminative features while learning from decentralized datasets. Up to date, there were some research on both reproducibility of different GNN models and federated learning separately. A recent study investigated and quantified the reproducibility of various GNN models, and another study proposed a framework which identifies the best data-driven feature selection method for boosting reproducibility in classification tasks. However, they cannot handle decentralized datasets. On the other hand, a novel work that brings an efficient solution by allowing the training of one single model while using decentralized datasets without collecting all of them into one single dataset. But federated state-of-the-art methods didn't investigate the reproducibility of GNN models. To boost the model accuracy, handle decentralized datasets, and identify the most reproducible discriminative features, we federate GNN models. Federation allows local models to predict more accurately by using a global model, which communicates with local models. Local models send their locally learned weights, and global model averages all collected local weights and broadcasts them accordingly. We repeated this operation for m different GNN models with h local datasets. To quantify the reproducibility of two models, we first extract the absolute values of corresponding feature weights and select the top k discriminative features with largest weights. Then, basically calculate the overlap ratio of the most discriminative features. After federated training for each model with medical data, we calculate the GNN to GNN reproducibility matrices for each hospital. Each node of these matrices presents the reproducibility scores of two different local GNN models. We then construct the global reproducibility matrix by averaging all hospital-specific reproducibility matrices. Finally, we consider the final matrix as a graph where the GNN models are its nodes. We use the highest node strength to select the most reproducible global federated model. The selected model is then used to identify the most reproducible biomarkers by considering the absolute values of the learned biomarker weights. We evaluated our framework using different types of datasets. The connectomic ASDNC dataset contains 300 subjects equally partitioned between autism spectral disorder and normal control. The dataset contains brain connectivities from both right and left hemispheres. The brain connectomes extracted from the Abide public dataset. The connectivity weight encodes the average morphological dissimilarity in cortical thickness between two cortical regions of interest. Additionally, we evaluated our framework on two large-scale biomedical image datasets named Pneumonia MNIST and Breast MNIST, which are retrieved from MedMNIST public imaging dataset collection. We used 1,000 subjects equally partitioned between normal and pneumonia classes from Pneumonia MNIST dataset. Each subject represented by a 28 by 28 X-ray image. Finally, we used 546 subjects from Breast MNIST dataset. 399 subjects belong to normal class and rest of them belong to malignant class. Each subject represented by a 28 by 28 breast ultrasound image. We divided each local dataset to two independent datasets split into 2/3 and 1/3, where we used these datasets for training and testing respectively. We used two state-of-the-art GNNs for the classification, which are GCN and diffpool. We benchmark our framework by comparing federated models with non-federated ones in terms of model accuracy and reproducibility scores. We trained baseline models without any federation, and these are the accuracies that we obtained. When we used federated learning, we noticed that the accuracy is boosted significantly across all datasets and all GNN models. We obtained the reproducibility matrices of non-federated baseline models and federated models. We observed 2% boost in the reproducibility score of ASD and CRH as highlighted on the figure. Additionally, we observed 8% and 5% increases for the ASD and CLH and pneumonia amnest datasets. However, a slight decrease was observed when we evaluated our framework with the breast amnest dataset. Using the average reproducibility matrices of ASD and C datasets, we identified the most reproducible connectomic biomarkers. The figure shows the absolute value of the right hemisphere biomarker weights learned by the most reproducible global GNN model, which are the average of locally learned weights. According to results, the insula cortex and lingual gyrus are selected as the most reproducible biomarkers. For the left hemisphere, the insula cortex and lingual gyrus are re-identified as biomarkers distinguishing between ASD and NC, as shown in the figure. In conclusion, in this work, we introduced the first framework investigating the reproducibility of federated GNN models with application to classifying medical imaging and brain connectivity datasets. Our framework solves the problem of decentralized data while increasing the both model accuracy and reproducibility scores, and can identify the most reproducible biomarkers. In our future work, we aim to evaluate our framework on more heterogeneous datasets and a large pool of GNN models, and design novel reproducibility measures, not only based on discriminative feature overlap. Feel free to check our recent review paper on GNNs in network neuroscience, covering recent GNN architectures for brain connectivity integration, classification, super resolution, and more. You can also visit the GitHub repo of the paper. For more, please visit us at basira-lab.com. Thank you for your attention.